On November 11th, 2025, at the exact moment 3I/Atlas skimmed past its perihelion, something anomalous occurred. Its orbit abruptly deviated from the trajectory that every model had predicted with near absolute precision. It wasn't a change in brightness, nor a gas outburst, but a genuine redirection, small yet unmistakable, enough to trigger immediate alerts from JPL's algorithms. In the dead of night, the orbit tracking team in Pasadena had to issue an emergency ephemeris update, disrupting all standard procedures because the data refused to align with any natural force model. No one knew what had acted upon 3I/Atlas at the instant it brushed closest to the sun. All they knew was one thing: something had changed. And like every great story that begins in silence, this deviation opened a mystery that no scientist could ignore. Before everything turned strange, all orbital models of 3I/Atlas, from JPL Horizons, ESA Gaia, to independent astrometric measurements, agreed that the object would follow a stable hyperbolic path. With no hint, it would behave unusually at perihelion. For weeks, observational points had lain perfectly on the forecast line, with errors at the milli-arc-second level, so tiny that astronomers almost believed Atlas was the most predictable interstellar object ever discovered. Yet right after the moment of November 11th, 2025, as Atlas swept past perihelion, the data began revealing the first signs of anomaly. Its actual coordinates no longer sat exactly where predicted, but shifted by a small yet distinct amount. More alarming was that the deviation wasn't random. It had a consistent trend, growing over time, forming a new motion vector, as if Atlas were under a tiny but directed ounce of force. Orbital models instantly became useless. Each ephemeris had to be frantically updated overnight just to keep pace with the motion Atlas was generating on its own. And when ground stations on Earth and Mars simultaneously confirmed the same offset, every safe explanation, like data noise, equipment error, or measurement inaccuracy, became meaningless. This wasn't random fluctuation. This wasn't a bad reading. This was a real orbital change, occurring right after perihelion, a phenomenon no interstellar object had ever displayed before. And then, before the question, what acted upon it, could even fully form in anyone's mind, the first imaging data from SOHO began pouring in. And that was when the true scientific shock hit. If you've ever seen coronagraph images, you know what they look like. The sun blocked by a dark mask, surrounded by the corona, and tiny bright spots, where comets typically appear with a fairly symmetrical coma and a straight dust tail, obediently pointing away from the sun. Everything follows simple logic: solar radiation and solar wind push material in directions we can predict with equations. But when 3I/Atlas appeared, all that intuition shattered. In the initial frames, its coma wasn't evenly round, but stretched to one side, distorted as if the entire surrounding gas envelope were being yanked sideways, like a balloon squeezed off center. Strangely, this pull didn't align with the radial direction, the line connecting it to the sun, nor with the solar wind direction at that moment, which plasma instruments had measured clearly. Simply put, it wasn't obeying solar forces. When corresponding frames from stereo A and stereo B were downloaded, the picture grew even more unbelievable. This time, not only was the coma deformed, but the plasma tail, the ionized tail, often seen as a compass for solar wind direction, was tilted at an unusual angle. If you imagine it as a thin smoke ribbon blown by wind, here, instead of flowing with the breeze, the ribbon was pulled diagonally by some other force. This offset didn't match any radiation pressure model or solar wind structure in the data. Researchers did what they always do first with an overly strange phenomenon: doubt the data. They rechecked the image processing pipeline: dark frames, bias, flat fields, lens correction errors, cosmic ray noise, everything. But while they were busy blaming the system, another detail became impossible to ignore. 3I/ATLAS had no dust tail. Not a single dust streak trailed behind it, like well-behaved comets do. All they saw was a stretched coma and an anomalous plasma tail, with zero signs of dust streams that could act as material jets generating thrust. This was the key point. If you want a natural comet to redirect itself with a strong outgassing burst, you need a substantial asymmetric ejection, water, CO, gas, or dust. Yet here, in the clearest frames, there was no sign of a major dust jet, just gas, very thin gas. Gas without enough momentum to explain the force required for the orbital shift the trackers measured. At this point, cross-verifying data became the absolute priority. No one wanted to be the first to stand before the scientific community and say something is pushing an interstellar visitor off course. So, group by group, they accessed data from other stations. GOES 19, with its unique viewpoint, quickly became a crucial piece. Its coronagraph images, taken at different times and optical conditions, reproduced the exact same picture. Coma stretched in the same direction, plasma tail, tilted at the same angle, no dust tail. When three independent systems, stereo, GOES all told the same story in unison, the chance of imaging artifact was virtually eliminated. You can imagine the atmosphere, then in control rooms and labs, stretching from Europe to America, people accustomed to the universe occasionally teasing humans with odd phenomena, still paused longer than usual before their screens. The plotted orbits no longer matched 3I/ATLAS's real position. The calculated force vectors from solar radiation, solar wind, non-gravitational effects from sublimation, all failed to connect with the coma distortion they were seeing. If you were sitting there, you'd see arrows on the screen, representing expected forces pointing one way, while the plasma streak and comet shape pulled another. That small gap, the mismatch between prediction and reality, was where the mystery began. By this point, every easy explanation had burned out. You couldn't say sensor error when three systems in three different positions gave the same result. You couldn't say dust jet when there was no dust tail. You couldn't say unusual solar wind when plasma data didn't support it. What remained was an uncomfortable void in scientific thinking. Some force was acting on 3I/ATLAS in a direction outside our familiar toolkit. This was the foundation of the first scientific shock. The moment those seemingly routine coronagraph images turned into visual proof that an interstellar visitor's orbit had been bent right before our eyes. And from that second onward, the question was no longer just how much did it deviate, but a far larger one. Why is there something in the universe that can do this? But the shock from stereo and GOES 19 was only the beginning, because the most critical evidence, the evidence that forced the entire astronomy community to abandon any notion of data noise, didn't come from Earth, but from Mars. At a completely different distance and viewing angle, two orbiters, MAVEN and Mars Reconnaissance Orbiter, IMASHU, inadvertently became the second witnesses to the event. If the near-Sun coronagraphs showed us a distorted plasma shape, MAVEN and IMASHU provided what no Earth-based instrument could: the real-time positional change of 3I/ATLAS against its predicted orbit, observed from an entirely different vantage in interplanetary space. MAVEN, with its plasma sensors and spectrometric cameras, recorded a small but clear shift in 3I/ATLAS's position relative to the NASA ESA consensus ephemeris. It wasn't just a bright spot off by a few pixels on a sky map, it was a trending series of offsets lasting hours, not a glitch that appeared and vanished. That meant ATLAS's velocity vector hadn't deviated once. It kept deviating, as if under an asymmetric force for a sustained period. IMASHU, with its high-resolution optical imaging, also captured a sequence of ATLAS positions across multiple frames. The tiny bright dots, when connected, traced a path that didn't match the pre-perihelion hyperbolic curve. And when two spacecraft in entirely different Mars orbits produced the same result, it allowed scientists to say something they're extremely cautious about. This wasn't display error, sensor inaccuracy, camera pointing mistake, or calibration issue. This was reality. And then, as if to drive a final nail into every skeptical argument, the two rovers on Mars's surface, Curiosity and Perseverance, recorded 3I/ATLAS's sky position and matched the anomalous tracking from MAVEN and IMASHU. Though designed for Martian geology and atmospheric missions, both rovers have basic astronomical observation capabilities for calibration and star sightings. At the time ATLAS passed perihelion, both were in windows to observe the night sky and captured frames containing ATLAS's bright point. Those images, after processing and comparison with standard ephemeris, showed the point in the wrong place, and crucially, it deviated in the exact direction indicated by MAVEN, IMASHU, OSOHO, Stereo, and GOES 19. One rover could be wrong. Two rovers wrong in the same direction is highly unlikely. Four Mars orbit instruments wrong in the same direction is nearly impossible. Six systems from two different planets using different observation mechanisms, all giving the same answer, left no doubt this was real measurement. With data from Earth, near-Sun space, and Mars combined, astronomers could now build a precise timeline. The deviation vector didn't appear once and stop. It evolved continuously for dozens of hours, then faded. This eliminated an entire suite of hypotheses, not a cosmic ray hit, not a noise spike, not a hot pixel, not telescope alignment error, not thermal drift, not any of the usual engineering glitches. This wasn't noise. It had structure. It had direction. It persisted over time. It ended over time. And it produced a change large enough to throw off the entire ephemeris used to track ATLAS. At this point, the question in mission control rooms was no longer, is something wrong with the data, but what acted upon it? If SOHO and Stereo showed a pulled plasma tail, MAVEN provided local plasma data, proving solar wind couldn't be the cause. If IMASHU confirmed positional offset, Perseverance and Curiosity reinforced that this was a three-dimensional space deviation, not a projection artifact. And from there, a conclusion began to emerge. This was not noise. It was a maneuver-like shift. A natural comet has no engine. An interstellar object has no reason to change course. A billion-year-old ice rock doesn't suddenly behave like a probe adjusting its trajectory. And so on Mars, a cold, barren world humans have yet to walk, silent data streamed back from robotic spacecraft became the most definitive witness that 3I/ATLAS had done what no interstellar object ever had. It truly changed direction. There was no way to deny it, no excuse to blame equipment. The truth was written across Mars's red sky. And from that moment, the story of 3I/ATLAS was no longer about a peculiar comet. It was about an object from beyond the solar system, exhibiting behavior science had never seen. Of course, once the data from both Earth and Mars was overwhelmingly clear, the scientific community's first reflex wasn't to leap to bold hypotheses, but to exhaust every familiar physical explanation for the phenomenon. Because if an interstellar object can redirect itself, either the physics we use is incomplete, or we're facing an extraordinarily rare exception. And so, natural hypothesis after natural hypothesis was brought to the table, dissected, and ultimately discarded one by one. The first, simplest, and most common was outgassing, the sublimation of surface material, creating a small thrust that nudges the orbit. This mechanism had explained Oumuamua's odd motion, so it was the prime candidate when Atlas shifted. But when parameters were plugged into models, the first issue was force magnitude. Even assuming Atlas could sublimate dozens of times more than an average solar system comet, the resulting thrust was still far too weak for the observed orbital deviation. And even artificially pumping the force to absurd levels couldn't produce the deviation direction seen in SOHO or MAVEN data. Outgassing is a mechanism whose direction depends on solar position. Material escapes more from the hot side, less from the cold, so the net force always trends in fairly predictable ways. But for 3I/ATLAS, the deviation direction was completely opposite to surface thermal models. In other words, even sublimating harder than any known comet, it couldn't deviate that way. The second hypothesis was radiation pressure, solar photon momentum. This is the force artificial solar sails use to maneuver, and it's real, measurable, calculable. But the problem with radiation pressure for ATLAS wasn't force size, but timing. Solar radiation force builds as the object nears perihelion, peaks there, then falls. If radiation pressure were the cause, ATLAS's velocity change would follow a smooth, continuous curve matching solar energy input. But MAVEN and SOHO data showed the deviation starting right after perihelion, not before. If the sun were responsible, the shift should have begun earlier, as light and radiation ramped up days before closest approach. In short, radiation pressure didn't match the timeline. That killed the hypothesis the moment the timeline was checked. Next came a more complex mechanism, plasma-solar-wind interaction, where solar wind bends the ionized tail. Plasma tails often curve under solar wind, sometimes oscillate, sometimes turbulence from magnetic fluctuations. But all these effects act on the plasma tail, not the comet's nucleus, the body itself. Solar wind is powerful but extremely low density. It can whip the plasma tail around, but the momentum it can impart to a solid nucleus is negligible. If ATLAS's core is a mountain-sized ice rock, solar wind is like breathing on it. It can't produce any significant velocity change. MAVEN measured solar wind speed and density at the anomaly's exact time, and those numbers were enough to rule it out entirely as the cause of the observed redirection. So plasma wind was crossed off. Another hypothesis involved internal gas jets, pockets of volatiles deep under the crust, heated until they explosively vent, creating thrust. Many comets do this, producing geyser-like jets. If true, ATLAS should show strong asymmetric gas columns. But two problems. First, ATLAS had no dust tail, meaning any strong jet would drag dust along, forming a dust tail, but none was seen. Second, a jet strong enough from depth would cause anomalous surface heating, producing a clear infrared signature. JWST and NEO-WISE recorded no corresponding temperature spike for a vent powerful enough to alter the entire object's velocity. Infrared data was cold and even monotonously stable, making jet models absurd. In other words, a jet strong enough to push ATLAS would leave a clear thermal trace, but there wasn't one. At this point, researchers turned to hybrid models, combining multiple small effects, hoping their sum could recreate the deviation vector's direction and magnitude. But every model hit at least one of three flaws: 1 force too weak, 2 direction wrong, 3 timing off. Nearly every equation fell into a core paradox. To match the recorded orbital shift, a natural mechanism had to be both larger than any known comet, precise enough to produce a specific deviation direction, and occur within a narrow hours-long window after perihelion. And here, an uncomfortable truth became clear. Every natural explanation had a problem. Not that they couldn't explain part of it, but no single mechanism explained all the data at once. Outgassing explained weak force, but not direction. Radiation pressure explained general direction, but wrong timing. Plasma wind explained tail shape, but couldn't move the nucleus. Gas jets explained asymmetry, but not the missing dust tail and stable temperature. And in the gap left by natural mechanisms, a question began to form, small at first, then growing with each ephemeris update. If this isn't the result of familiar physics, then what is it? No one wanted to jump to dangerous hypotheses, but science had no choice left but to accept that 3I/ATLAS, the third interstellar object in history, had just performed a behavior we cannot explain with everything we know about nature. And from that moment, the story shifted into territory science always hesitates to enter, where the impossible must be weighed as real possibilities. And it was precisely in the gap that familiar force models couldn't fill that scientists were forced to revisit data they had recorded for weeks before perihelion, unusual chemical signatures that everyone initially thought were just characteristics of a strange interstellar comet. But when the orbit shifted, this data suddenly became more important than ever, because if mechanical forces couldn't explain the deviation, the secret might lie in the atmospheric and spectral fluctuations Atlas had shown long before approaching the Sun. In the weeks leading up to November 11, 2025, observers recorded continuously rising levels of gas molecules like C this, NH this, NCO this in 3I/ATLAS's spectrum. This wasn't unusual for comets in general, but with Atlas there were two odd points. First, the increase in these molecules far exceeded what was expected from an object originating outside the solar system. Second, and more importantly, all that intense sublimation produced absolutely no sign of a dust tail. Ordinary comets, when sublimating strongly, generate clouds of solid particles that get carried along, forming a dust tail. But ATLAS had only gas, a huge amount of gas that caused its brightness to fluctuate wildly, yet still failed to produce even a dust streak. This had been puzzling from the start, but only when the orbit changed did people begin to look back and ask, so what exactly is all that gas doing inside its nucleus? ATLAS's brightness also didn't behave as models expected. In the week before perihelion, its brightness rose faster than predicted, then slowed, then surged sharply in the hours just before reaching closest approach. This brightness wave had led some research groups to speculate that internal pressure restructurings were occurring inside ATLAS, cracking ice layers, deep gas pockets bursting open, or even internal material regions being reactivated as temperature rose. But throughout that time, no one thought the gas and brightness fluctuations could be linked to an orbital redirection, and in fact, even upon re-examination, the brightness changes themselves didn't provide enough force to generate an orbital deviation vector. The spectral fluctuations indicated strong chemical activity, but the mechanical force generated was too small to push a nucleus hundreds of meters to kilometers in size. So when ATLAS changed direction, many researchers immediately ruled out brightness and spectrum as direct causes. However, what made this data intriguing wasn't its force, but the unusual rhythm of the fluctuations. If someone only looked at total brightness, they'd think it was a comet undergoing minor outbursts. But examining the molecular spectrum closely revealed a more complex picture. CO concentrations rose in bursts, interspersed with sudden NH spikes, while CO remained relatively stable. This wasn't a familiar natural spectral pattern. The alternating rise and fall cycles of different molecules made ATLAS seem to be undergoing internal activity in rhythms, not random sublimation. A natural object rarely exhibits cyclic behavior on such short timescales, especially in the harsh environment near the sun, where everything usually becomes chaotic rather than ordered. That was why scientists began to grow concerned. Strong internal chemical activity in ATLAS could create pressure changes, and pressure could cause outbursts. But the outburst direction, completely incompatible. If internal pressure spiked suddenly and material escaped, the thrust would depend on where the surface ruptured, and that should leave clear traces, a hotter coma section, anomalous infrared temperature, or at least a thin dust tail. But there was none of that. JWST, no eyes, and many other infrared observatories all showed ATLAS's temperature rising very little, stable to an unbelievable degree, given the volume of gas it was releasing. This led to a paradox. If there was strong activity inside, why was the exterior so stable? And if the exterior was that stable, why did the orbit deviate? Some researchers hypothesized that the gas and brightness fluctuations were signs of internal restructuring, a process that could alter mass distribution and moment of inertia. But even a change in mass distribution could explain new sensitivity to external forces. It still couldn't account for the specific deviation direction ATLAS exhibited. There had to be an acting force, and if that force wasn't from outgassing, radiation, or plasma wind, where was it coming from? At this stage, the only thing the spectral and gas fluctuation data proved was 3I/ATLAS was not passive like other interstellar objects. It wasn't just an ice chunk flying through the solar system and leaving in silence. Inside it, there was activity, structured, cyclic activity, but too light to move the object. So this data wasn't the answer, but an uncomfortable reminder that 3I/ATLAS was profoundly anomalous on multiple levels: structure, chemistry, thermal, and now motion. What we saw in it before perihelion didn't explain the redirection, but gave the sense that 3I/ATLAS wasn't what we're used to calling a comet. And for that reason, this gas and light data, though unable to explain the acting force, still became a crucial part of the mystery puzzle. Something was happening inside this object, and it started long before the orbit changed direction. From here, the scientific story no longer focused only on what pushed it, but expanded to what's happening inside it. And that was a mystery no less frightening than the orbital deviation we had just witnessed. And it was precisely when the gas and brightness fluctuations showed Atlas wasn't entirely passive that all eyes turned to the one place capable of peering through layers of material, melted, recrystallized, and deformed over billions of years. The James Webb Space Telescope, JWST, had been tracking 3I/ATLAS for weeks before perihelion, and data that scientists previously treated as mere background information now became the key to unlocking one of the biggest secrets of this interstellar object: a radiation-hardened crust, 50 to 65 feet thick, a layer of material that no longer retained any primordial properties from where it was born. Analyses from NIRSpec and MIRI revealed that crust had been pummeled, penetrated, and continuously restructured by cosmic rays, high-energy particles from across the galaxy, for billions of years. We're not just talking simple erosion or weathering. Cosmic rays can break molecular bonds, rearrange crystal lattices, convert material from one form to another, and create compounds almost never seen in our solar system. What JWST discovered was truly shocking. Atlas's outer crust wasn't the pristine ice rock of an object from a distant star system, but a new structure, a composite material layer formed by cosmic radiation over billions of years. In other words, Atlas had been reshaped by the universe from the outside in, layer upon layer, until the surface JWST saw no longer carried much information about its origin, but reflected far more about the journey it had endured. But what troubled scientists even more was the crust's heterogeneity. JWST didn't see a uniform shell, but patches of different materials, interspersed like sedimentary layers, crumpled by time. Some regions harder, some more porous, some up to 65 feet thick, others only 50 feet or thinner. The crust varied not just in composition, but in density and energy reflectivity. This made Atlas an object with unusual moment of inertia. Unlike any solar system comet, applied to the redirection story, this meant that if any force, no matter how small, acted on Atlas's surface, the object's response would be highly unpredictable. Some areas absorbing energy strongly, others reflecting, some heat-resistant, others prone to cracking. This very unevenness increased the likelihood that Atlas could react abnormally to heat, radiation, or even internal volatile pockets. This was where the next hypothesis emerged. Beneath that mottled crust might exist volatile pockets, cavities holding gas, or easily vaporized material, compressed under pressure, and when the crust thinned at a certain point, they could burst like a small explosion, generating off-course thrust. The idea sounded reasonable, At least it fit with Atlas having no dust tail, but strong gas activity. But when modeled problems arose, such gas pockets would produce random outbursts, with direction depending on where the crust ruptured. Meaning if Atlas experienced a gas explosion, the orbital change would be chaotic, lacking temporal stability. But MAVEN and MRO data showed Atlas's deviation direction was stable, not wildly fluctuating, as outburst models predicted. Moreover, a deep volatile pocket rupture would leave a very clear thermal signature in infrared spectra. JWST rechecked all data before and after perihelion and found no hot spots of intensity, matching a material ejection large enough to cause the recent deviation. The second problem with the volatile pocket hypothesis was the precision of the deviation direction. A natural outburst produces random thrust, depending on rupture location, crack shape, and material depth. Yet Atlas's deviation occurred in a stable, smooth direction, lasting hours. This resembled intentional behavior more than a natural burst. Some researchers even exclaimed in closed meetings, "If this is a natural outburst, it's the most precise one I've ever seen." And that was why the volatile pocket hypothesis, though more plausible than outgassing or plasma wind, still couldn't explain all the data. So the biggest question began to rise, echoing the original script's point about internal structure. If the crust has been completely restructured by radiation, then what's beneath it? This was a question JWST couldn't answer. It could peer through a few dozen feet of crust, but not into Atlas's true core. That core, the part the universe hadn't destroyed, hadn't distorted with cosmic rays, the most primordial part of a star system lost billions of years ago, might hold all of 3I/Atlas's secrets. If that core were lighter than we think, or denser, or hollow, or contained internal heat pockets, or materials completely absent from the solar system, anything could happen. As one scientist described, we're looking at an object whose exterior belongs to its journey, but whose interior belongs to its birthplace, and we don't know how different those two parts are. Notably, though JWST couldn't provide a complete explanation, it inadvertently made the problem more dramatic. That 65-foot crust, instead of explaining the redirection, made the question harder to answer, because if the crust was deformed to an unnatural degree, was the inner core still pristine, or was that core the cause of the bizarre behavior? When piecing together the facts, deformed crust, heterogeneous structure, possible volatile pockets, absence of dust tail, and unusually precise deviation, people were forced to face an uncomfortable truth. JWST might have shown us everything it could see, but what it couldn't penetrate was the most frightening part. And so at the end of the JWST data section, no answer appeared, but a larger, deeper question, carrying the weight of an entire interstellar mystery. Beneath this crust, what is really there? But if the radiation-pierced and restructured crust over billions of years still retained its shape, the next question was, how long did Atlas take to become this way? And right here, one of the most staggering details of the entire story emerged. Age estimates from various astronomy groups suggesting 3I/Atlas might have existed for 7 to 12 billion years, meaning older than the solar system, older than Earth, older than our own first planets. If true, Atlas wasn't just an interstellar visitor, it was a relic from the Milky Way's infancy, a fragment from when the universe hadn't yet reached the form we know today. Imagine this, when the solar system hadn't even sparked, when the galaxy's first stars were still gathering material to ignite, 3I/Atlas already existed, drifting through interstellar space, passing through ancient plasma storms, exposed to radiation streams far stronger than anything our sun could produce. It wasn't a young wanderer recently ejected from a nearby system. It might have begun its journey when the Milky Way was still a chaotic gas disk, when most of what we call modern astronomy didn't yet exist in physical terms. The fact that an object lasted this long, yet remained intact enough for us to observe its shape and properties, made many scientists pause and reflect. Usually, small comet-like objects are destroyed within a few 100 million years. Collisions, radiation, tidal forces, structural decay all form a long chain of mechanisms, ensuring they can't survive long. Yet Atlas was here, retaining a structure durable enough to endure the galaxy's most extreme environments. This led some cosmic material experts to ask, how can an object this size survive so long without shattering? An interstellar traveler over billions of years must endure countless micrometeoroid impacts with interstellar dust, magnetic and plasma effects from thousands of stars, intense radiation from supernovae, and continuous surface alteration by cosmic rays. If Atlas survived all those processes, it must possess durability far beyond any ordinary comet model. Measurements from JWST and thermal analyses from NEOWISE showed Atlas had few large surface fractures. The unusual outer crust, harder, mottled, thin in places and dense in others, seemed not to harm overall structure. Even cosmic rays, which can gradually destroy material over time, had inadvertently created a natural armor many times harder than original ice, making Atlas resemble a nucleus encased in a shell that survived every era. But if that crust was a product of the journey, how extraordinary must Atlas's initial structure have been to maintain stability through such brutal forging? Some models even hypothesized Atlas might have been compressed in the galaxy's early phase, when giant molecular clouds created pressures so immense that small objects were squeezed into denser forms. Other hypotheses suggested Atlas could be the remnant of a destroyed planet, or an ice rock fragment that underwent mild heating before being ejected from its home system. But no matter the model, one undeniable common point: Atlas wasn't a normal comet. Its durability, proven by a billion-year journey without disintegration, led many researchers to lean toward the idea that Atlas's structure must be fundamentally different at its core. It might be denser than ordinary comets, or have unusual crystal configuration, or a much harder solid core than the radiation-reworked ice layers. Its core might also contain material layers never observed in the solar system. Another aspect that couldn't be ignored was Atlas's path through interstellar space. Backward orbital simulations showed its trajectory wasn't tied to any recent star system. Instead, it seemed to have drifted through the Milky Way's outer regions, where matter density is low but radiation environments are extremely harsh. Many astronomers described Atlas's orbit as a galactic pilgrimage, a journey so long that most objects would be completely destroyed before halfway. But Atlas didn't. It survived, and it arrived here, drifting into our solar system, like a remnant from an era modern science can only simulate. When combining ancient age, extraordinarily long journey, altered structure, yet retained integrity, Atlas carried a completely different feeling, not just strange, not just incomprehensible, but weighty, as if it carried the galaxy's entire history, contained within cosmic ray-melted crust, within a distorted core we haven't seen. A cosmic athlete that lived too long, a survivor of things no natural object should endure. And when an object like this, older than the sun, having passed through regions humanity can't imagine, suddenly changes direction right before our eyes, it's no wonder a sense of galactic-level mystery immediately enveloped the entire story. Because if 3I/Atlas's journey lasted billions of years, yet it only changed direction here, as it passed through the solar system, then the deepest, most frightening, and hardest to answer question began to emerge. Why now, and why here? But it was precisely when the age and journey of 3I/Atlas revealed a galactic-scale mystery that the biggest problem lay in a very small point. So small that only meticulous numbers in telemetry tables revealed it. The lob of Atlas was tiny, almost negligible by orbital mechanics standards, yet its deviation direction was clear, stable, and lasted for hours. This was the key paradox. In celestial mechanics, an object can experience a very small lob, But if the acting direction is sustained over a sufficient time, it will produce a measurable orbital deviation in three-dimensional space. That meant Atlas didn't receive a big kick, but a very small directed force acting continuously in the hours right after perihelion. Data from MAVEN, MRAO, and GOES 19 all showed the same thing. The velocity change was only a few millimeters to a few tens of millimeters per second, numbers too low to notice if it were an ordinary comet, but the direction of this force matched no natural mechanism. In orbital physics, when an object experiences non-gravitational effects, we typically consider these force components d term from photon pressure, drag from radiation, angular drag from plasma, mass shedding from sublimation, and in comets, asymmetric outgassing jets. But for Atlas, when each force component was cross-checked against each time frame, all fell into cannot be the culprit. Photon pressure, light pressure, always pushes the object radially outward from the sun. This is a force calculable precisely based on albedo and object shape. If photon pressure were the cause, the deviation direction would nearly align with the radiation vector. But Atlas deviated at an angle nearly 40 degrees off this axis, a discrepancy too large to dismiss as noise. Angular drag from solar wind plasma also didn't fit. MAVEN measured plasma density and direction at that moment, and simulations of plasma tail lag showed solar wind had nowhere near enough momentum to affect the nucleus. It was only enough to bend the tail, not push the entire object off course. Mass shedding, mass loss from sublimation, happens a lot in comets near the sun, but Atlas had no dust tail, meaning it wasn't losing mass in a way that generates thrust. If it were, it would leave clear signatures in infrared spectra and geometric brightness, but there were none. All this forced researchers to test the final model jet outgassing. This was once the popular explanation for Oumuamua, the first recorded interstellar object. Back then, part of the community argued Oumuamua's unusual acceleration came from sublimating water or CO from a small crack, even without a dust tail. But 3I/Atlas not only lacked a dust tail, it showed no temperature spike corresponding to a strong outburst, and no pressure fluctuation large enough in molecular spectra to produce a jet opposite the orbital vector. In other words, if Oumuamua was a hard puzzle, Atlas was impossible, because at least with Oumuamua, there were some brightness fluctuations, minor spectral changes, and an elongated shape to justify an asymmetric outgassing model. But Atlas showed strong gas changes, but no temperature change fluctuating molecular spectra, but no dust creation, and most crucially, none of the fluctuations could produce the OLV direction MAVEN measured. When natural force models couldn't explain its behavior, orbital mechanics experts began doing something they rarely do, directly comparing 3IATLAS to Oumuamua, and this was where things got more serious. Like Oumuamua, Atlas went through a phase where its acceleration vector didn't match gravity. Like Oumuamua, Atlas had no dust tail despite clear gas activity. Like Oumuamua, Atlas exhibited small but directed delta, a type of acceleration matching no natural pattern. And like Oumuamua, Atlas showed a clean shift, smooth deviation, no jitter, no oscillation, something natural comet outburst, never sustained long. But here, Atlas did something Oumuamua didn't. Its data showed signs of pattern, a lawful directional change trend, not chaos. MAVEN recorded the deviation vector over hours, and throughout that time the vector didn't fluctuate wildly like a surface-cracked comet, but stayed stable, then gradually decreased. Past simulations showed Atlas Ebos wasn't a single kick, but a continuous all-above process, like experiencing a sustained force rather than an impulsive one. In orbital mechanics, there's a very specific definition for this, continuous non-gravitational acceleration, and in the context of natural bodies, that almost never happens. In natural comets, every outburst is impulsive on-off. There's no such thing as an outburst maintaining fixed direction for hours, yet 3IATLAS did exactly that. This led a JPL researcher to blurt out in an internal meeting, "This looks less like a kick and more like a steer." And of course, no one dared go further than that statement. But data doesn't lie. In the vector plots M sent back, Atlas, a deviation force, seemed not merely a natural reaction. It had pattern, not fully artificial, but not fully random either. It had internal logic, though very faint, very subtle, but present. When orbital analysis groups at ESA, JAXA, and NASA placed ATLAS data on the same coordinate system and compared it to orbital models of thousands of tracked solar system comets, they all realized one thing: no model reproduced this Atlas F curve. No natural mechanism in the familiar force catalog could push 3I/Atlas in that direction at that time with that stability. And from the failure of orbital mechanics to recreate the phenomenon, a new question arose, first whispered, then becoming an obsession. If the deviation has pattern, where does that pattern come from? A pattern means cycle, stability, logic. A pattern means repetition. A pattern means the force isn't entirely random, and in the natural universe, random forces are normal, but a pattern means something else. This wasn't a conclusion, this was just where the question began. But from this moment on, no one could look at 3I/Atlas as an ordinary interstellar comet anymore. Its orbit, tiny, silent, but deviating in a direction shaped like a decision, became the first milestone in history, the moment an ancient object, older than the sun, after billions of years of silence, suddenly performed a behavior no familiar law could fully describe. And that opened the door to the most mysterious part of the entire story. But it was precisely when the question of pattern began to emerge that the atmosphere in the scientific community shifted from cautious skepticism to a new state, an intellectual fear, that strange feeling that only arises when data forces humans to stare directly at a possibility they don't want to acknowledge. And like every major scientific crisis in history, the community immediately split into factions. The conservative faction, those who believed in the endurance of decades-old physical models, spoke up first. They argued that 3I/Atlas orbital deviation, no matter how strange, could still be explained by a natural mechanism not yet fully described. Maybe a rare plasma interaction. Maybe the unusual radiation crust caused the nucleus to react asymmetrically to heat. Maybe an intrinsic material we've never seen, creating a moment of inertia distribution leading to a directed all-war. This is an interstellar comet, they said. It's unlike anything in the solar system. Strange behavior is reasonable. But that argument grew weaker when confronted with data. Scientists in this faction were forced to stretch the list of natural hypotheses to the edge of absurdity. Maybe a volatile pocket at exactly the right angle, maybe a deep core chemical reaction, maybe perfectly timed unusual solar wind. But the more they spoke, the more they felt the pressure of reality. No natural model reproduced the deviation vector. So on paper, the conservatives continued defending classical science, but in closed meetings, awkwardness appeared. In contrast, the progressive faction, those willing to accept data, even if it pushed them out of their comfort zone, began saying things previously only whispered. Some JPL and Harvard researchers, after viewing Maven's vector plots, noted in internal emails phrases like intended directionality or non-random steering. No one dared write maneuver, but they were circling it. They talked about the Vogt curve shape, talked about deviation vector stability, talked about the smoothness of the time-based change, and most importantly, they talked about precision. Nature isn't precise. Nature is powerful, chaotic, asymmetric, and sometimes brutal. But nature rarely produces motion resembling sustained intent. Nature doesn't move an ancient object in a fixed direction for hours. Nature doesn't maintain a stable deviation vector, then let it linearly decay. A few in the progressive faction, not all, admitted that if they saw this oboe plot without knowing its source, they'd think it was simulation data from a probe using low thrust for trajectory correction. And this was why A.V. Loeb's name resurfaced, just as it had in the 1I/Oumuamua story. Loeb, the one willing to say what most feared, publicly demanded NASA release full tracking data for 3I/ATLs, including raw ephemeris, DSN raw data, MAVEN and MRO telemetry, and all explanatory models NASA was testing. In an online talk, he said a line that made many uncomfortable, but undeniable. If the data shows anomalous motion, our job isn't to find reasons to ignore it, but to understand it. This was the spirit the original script referenced, not ruling out possibilities just because they inconvenience belief systems. Loeb's demand immediately triggered fierce backlash from conservatives who feared public data release would lead the public to jump to alien conclusions. But at the same time, progressives saw it as a logical step. If the data was fully natural, release would prove it. If not, at least science would have enough information for sophisticated analysis. Right in this chaos, the SETI faction, those who study extraterrestrial intelligence, seriously, cautiously, and scientifically, began to speak. The SETI faction didn't declare 3I/ATLAS a probe. They certainly didn't say it was artificial, but they emphasized what the community had forgotten. Interstellar objects are things we've only observed 3 times in history, and if there's a reasonable place to look for evidence of extraterrestrial intelligence, it's in objects moving between star systems, not because they look like spacecraft, but because interstellar space is where the most advanced technology could survive longest. When they looked at ATLAS's Loeb, they didn't conclude. They only said no one is allowed to rule out non-natural possibility when data doesn't fit natural models, and that was enough to split the community into 2 clear halves. One half wanted to protect the purity of classical science. One half wanted to expand the framework of thought to not miss what could be humanity's greatest discovery. But despite the divide, there was one point everyone saw, but no one wanted to say publicly. 3I/ATLAS's behavior resembled a maneuver, not a big maneuver, not something loud or obvious, but a small, subtle, continuous course correction, like an orbital adjustment using ultra-low thrust, something typically used in satellites or probes with ion drives. Of course, no one dared label artificial on a 712 billion-year-old object, but they couldn't deny that natural physics had never shown such directed behavior. The divide in the scientific community deepened as new data kept pouring in. Internal meetings at NASA, ESA, JAXA were filled with phrases like, "We don't have the full picture yet, don't rule anything out, and be prepared for the possibility we're wrong." No one said 3I/ATLAS was a probe, but no one dared say the opposite either. And right on that fragile boundary between scientific pride and the fear of admitting something beyond understanding, the story of ATLAS shifted from an orbital anomaly to an intellectual test for all humanity. Because if an object older than the sun, wandering the galaxy for billions of years, suddenly changes direction as it passes through the solar system, the question is no longer, what did it do? The question is, why did it do it? And this was the point where intellectual fear began to replace pure curiosity, when some started realizing that sometimes the scariest thing isn't the answer, but the fact that the question exists. But if the debate within the scientific community was where intellectual fear began to form, the next part of the story was precisely where all eyes were forced to turn toward the future. Because even though 3I/ATLAS had changed direction once, the most important question wasn't what it had done, but what it would do next. And that was the part that kept astronomers awake more than any data collected so far. From all existing simulations, from feather measurements to plasma tail analyses, the scientific community was forced to consider three main scenarios, three future branches, each carrying different scientific implications, even leading to completely opposing conclusions. The first scenario, Atlas returns to normal behavior. This was the scenario the conservative faction hoped for most, and the most acceptable under traditional scientific logic. If Atlas stabilized its trajectory, returned to the predicted post-perihelion hyperbolic path, and produced no further bulge, the astronomy community could argue that the recent deviation was the result of a rare combination of natural factors: an outburst without thermal signature, an extreme plasma interaction, and internal deformation creating asymmetric force. Of course, none of those hypotheses were complete, but if Atlas stopped deviating, science could close the event as an unexplained but natural anomaly. This had happened with many other comets, strange behavior appearing for a few days, then vanishing forever. If Atlas followed this branch, the story would remain intriguing, but it wouldn't threaten to overhaul our entire thinking about interstellar objects. It would be like a rare phenomenon, an unexplained kick, then fade into obscurity like anomalies recorded but lacking data to decode. However, in JPL's long-term simulations, only about 40% modeled this scenario. That wasn't a small number, but not enough to reassure anyone. The second scenario, Atlas continues deviating along the same vector. This was the scenario deeply dividing the scientific community, because if Atlas kept deviating in the exact direction recorded by MAVEN and MRO, with Atlas still very small and stable, it would pose an entirely new question: where is that force coming from, and why is it maintaining such stability? In nature, all forces have fluctuations. Plasma is chaotic, outbursts are erratic, sublimation depends on changing temperature. No mechanism produces a light but temporally stable force vector. If Atlas continued deviating in the same direction, every passing hour would strengthen the argument that the deviation wasn't just an anomaly, but a process. And if it was a process, it carried an implication: something inside Atlas was controlling its behavior in a specific direction. This could still be natural. Core structural changes could cause prolonged asymmetric reactions, but the uniformity in Atlas' direction made natural arguments hard to sustain. Progressive researchers said bluntly, a directed TAV process lasting hours resembles control rather than random asymmetry. If Atlas followed this branch, it would be the strongest evidence in history that interstellar objects could possess movement mechanisms we've never described. The third scenario, a second maneuver, appears. This was the scenario making many scientists uncomfortable, because a second deviation, occurring at a different time, in a different or same direction, couldn't be explained by any existing natural mechanism. Two consecutive TAV-WUF, without corresponding thermal signs, without a dust tail, without plasma instability. No comet in history had done that. No natural object in millions of observations had ever shown behavior resembling orbital adjustment. If Atlas changed direction again, the scientific community would be forced to accept that either our physics was missing a piece too large to believe, or Atlas was performing behaviors we once thought only applicable to artificial probes. No one would say artificial, but skirting around it would be unavoidable. And if this happened, Atlas would become the turning point of all astronomy, a revolution forcing us to rewrite our understanding of interstellar objects. In all three scenarios, there was one common point: Atlas was entering the phase where what it did would determine how we interpreted all the data collected so far. This was the moment akin to the original script, post-perihelion, could be even stranger. And indeed, Atlas was moving into a region of space where we could observe it more clearly, while it was moving away from the sun and becoming less influenced. If any atlas appeared in this phase, it could almost certainly not be blamed on temperature or outgassing, meaning even a small deviation would carry 10 times the weight of the pre-perihelion one. That was why tracking teams at JPL, ESA, and JAXA all described this phase as the decisive moment. If Atlas passed through this region without anomaly, the story would quiet down. If it did, it would explode. And in this tense silence, as the world watched a tiny bright point against the dark sky, we realized that Atlas wasn't just a cosmic object, it was a test, a question. A milestone astronomy would reference for decades. Because now, the future of the story was no longer in scientists' hands. It was in 3I/Atlas's next behavior, and that made every received signal, every new measurement, every tiniest offset a crucial piece in a mystery that might be the greatest humanity had ever faced. As all those scenarios unfolded before our eyes, as the three future branches of 3I/Atlas hung suspended among the stars, like three doors leading to paths humanity had never walked, the final question no longer revolved around what Atlas would do, but around the true meaning of that initial redirection. Because no matter which scenario occurred, whether Atlas stabilized or continued deviating, whether or not a second maneuver appeared, the truth remained unchanged. An interstellar object's orbit had changed direction in a way incompatible with familiar physics. That didn't mean Atlas was artificial, didn't mean intelligence was controlling it, didn't mean we had witnessed something from another civilization, but it forced us to look into the darkness between laws, into the edges of models we long believed complete, and ask questions science had avoided for decades simply because they were too inconvenient. Because Atlas's redirection, even if so small, it only appeared on telemetry plots, was saying one thing very clearly: the universe might contain mechanisms science doesn't yet know. An object older than the solar system, reshaped by cosmic rays for billions of years, colliding through countless alien environments, yet retaining structure. An object producing no dust tail, but strong gas activity. An object experiencing a small but stably directed delta. An object wandering between stars, but only changing direction upon entering our solar system. All of that suggested a possibility hard for researchers to swallow. The universe isn't simple, it never was, and perhaps we were the ones who simplified it in equations, in models that sometimes reflected human confidence more than nature's true essence. But there was another possibility, and that was the one making everyone fall silent. This redirection could be something beyond the natural framework, not in a science fiction sense, not in the sense of a probe actively controlling its path, but in the sense that it was the result of a non-natural mechanism, a form of material organization or internal dynamics we've never described, a behavioral tendency that was systemic, not reactive, a pattern from within, not from without, an engine that wasn't an engine. This wasn't easy to say because it required accepting that human intelligence, with all its telescopes, simulations, and equations, was still just a child first seeing the ocean. We look at Atlas and assume we understand what it's doing. But if we were wrong from the initial assumption that Atlas must behave like a comet, then the entire story of natural force versus non-natural force became meaningless. Perhaps the universe was simply vast and ancient enough to contain object types our current intelligence couldn't yet classify. Perhaps Atlas didn't maneuver, it was just doing what objects of its class always do, and we didn't know because this was the first time we'd seen that class. But perhaps, just perhaps, Atlas had become the first object forcing modern science to seriously consider that not everything in nature is random. Some things might bear the mark of purpose. Not someone's, but the universe's own internal structure. And that possibility that Atlas wasn't just an ancient rock, but a form of information, made the entire scientific community, from the most cautious to the boldest, pause and reflect. As of now, Atlas was still slowly moving away from the sun, still leaving behind it the big question no one could fully answer. It might stay silent from here on, or it might change direction again, or it might reveal something inside its radiation crust as temperature dropped and structure contracted. No one knew. But everyone understood that the first redirection had set a milestone. From now on, every interstellar object entering the solar system would no longer be seen as a strange comet, but would be viewed with caution, as if checking whether the universe was sending another message. And so the ending of this story wasn't an answer, but a reminder. A reminder in the true spirit of the original, of humility before the cosmos. If the universe is testing whether we're capable of understanding it, can we answer? If you want to continue following the strange journey of 3I/Atlas and other mysteries from the universe, please subscribe so you don't miss any part. Thank you for joining, and see you in the next discoveries.